Hi everyone, this is Janine Co, aka Janine The Tutor. As you all know, right now is a difficult time for each one of us, whether you're in middle school, high school, or university. Many students and families are deeply affected by the recent school closure. And as a part of OneClass, we are very fortunate that we are able to adapt quickly, and we want to extend our helping hand to you students, so students across North America, because we want to make sure you stay on top of your studies. So we are offering daily classes for math and chemistry. And in addition, we are also offering and giving away 100,000 hours of free private tutoring. So if you're interested, make sure to scroll down below and book your time slot. So for today's class, we are covering the most popular Q&As on oneclass.com /homework help. And if you guys can see my screen, please let me know. So you should be seeing a question where it says how many protons, neutrons, and electrons are in a neutral atom of sodium. Okay, so this is ranked based on the most frequently asked questions. So as you can see, this student said that for sodium, in the neutral state, it has protons, which is 11, neutrons, 12, electrons, which is 11. So just as a recap, if you were part of my grade 11 chemistry class earlier this morning, I talked about the elemental symbol, which is atomic number and atomic mass. So that's in the form X. So this A right here is basically your atomic mass, just as a recap. And this Z is atomic number. Again, I just wanted to check in to see whether you can actually see my handwriting on top of this question. So this X is your element. Okay, so going back to sodium, so sodium is our element, and then they're saying that protons is basically 11. So that means that's your atomic number, because in the neutral state, atomic number equals the number of protons, right? So how do you find the number of protons or atomic number of sodium? So really, you all have to get your periodic table and make sure that you have that. So I'm just going to use this right now. Okay, hopefully you guys can see my periodic table, but I just wanted to show you that sodium is found here. Let me just clear that. Okay, sodium is found in group 1, which is right here. So it's atomic number 11, right? So that means 11, atomic number 11 is actually the number of protons, right? So P plus, because we know that protons are positive charges, right? Or positively charged, and that's 11. And then you have atomic mass, which is what we need to look for. So because it's in the neutral state, right, the number of protons equals the number of electrons. That's why we can say electrons is also 11. However, for neutrons, right, because we're looking for the atomic mass, we know that for sodium, again, going back to the periodic table, sodium is 22.99. Okay, that's where sodium is. Hopefully you guys can see that it's 22.99. So that means you have 23 for sodium, because it's 22.99, right? That's your atomic mass, so we can just round it to the nearest whole number, so that's 23. So for your neutrons, remember your atomic mass is basically a sum of the number of protons plus the number of neutrons, and that's equal to 23, right? So that means 23 minus 11 is actually equal to the number of neutrons, and that's going to be 12. So the number of neutrons is 12, and this is correct. So what they presented here on homework help is actually correct. Okay, so hopefully that was clear. This is nothing to stress about. Okay, so this is the second most popular question. So it's asking for which of the bond order is correct. So they provided so underneath that, if you can see, they provided a whole paragraph of answers, right? But I tell my students that I really prefer learning chemistry visually and also in text. So for this one, you'd really have to draw the molecular orbital diagram for you to really understand this. So that's what we're doing, because they don't really have any diagram, as you can see. Yeah, there's no diagram, so we need to make this better. Okay, so this is gonna be a long one, so just bear with me. Okay, so first of all, what's a molecular orbital, and what's the difference between Okay, so going back to my question, what's the difference between a molecular orbital and an atomic orbital, right? So that's what you have to ask yourself first. So a molecular orbital is a result of atomic orbitals overlapping, and that's why you get molecular orbitals, right? So for example, if you have F2, they would overlap, right? So two fluorine orbitals will overlap, and then they would form a molecular orbital. So that's basically what it is. So we have a molecular orbital here, and we have an atomic orbital right here, because it's composed of two atoms, right? So it's side by side. By the way, if you're from Western, this is a very popular question that I see a lot of students struggling. So yeah, pay attention to this, because now hopefully this will make sense. So you have atomic orbital, and then you have molecular orbital. So first of all, we're looking at fluorine in this case, and it's two atoms of fluorine, right? So we know that fluorine is actually found in group 7, which is right here. So group 7 is right here, if you can see my periodic table, and that's actually at n is equal to 2, right? Because it's period 2. Does that make sense? So if you look horizontally, you're seeing fluorine right here. So we know that fluorine is n is equal to 2. So we need to write that. So this atomic orbital and molecular orbital is for fluorine. And we know that this is n is equal to 2. So therefore, we're only looking at the energy level of 2, right? So when you think about the electron configuration, just at the n is equal to 2 level for fluorine, that means it's going to be 2s2, right? Going back to this. And how is it 2s2? Well, you're looking at lithium, right? 2s1, beryllium, 2s2, right? And then you have fluorine, which is 1, 2, 3, 4, 5, right? So that's 2p5, right? Because remember, these two are basically your columns for your s orbital, and then you have your p orbitals, which is on the right side. And we know that fluorine is found in p5, right? At n is equal to 2. So that's why it's 2s2, 2p5. And this is just for one atom of fluorine. But because there's two of them, it's also important for you to figure out how many electrons, specifically valence electrons, you have for diatomic fluorine. So valence electrons, right? Because we know that fluorine is found in group 7, therefore it must have, like, one atom of fluorine must have 7 valence electrons. And because you have 2 atoms of fluorine, that would be 7 times 2, which is 14. Does that make sense? So these are your crucial information. So these are the necessary information that you need to fill out your atomic orbital and your molecular orbital. So So this is 7 times 2, which is 14. And then first we have to draw our orbital diagram. And just remember that this is an increasing energy level, right? So starting from the bottommost part, that's your lowest energy level. As you rise up, your energy level increases. So for atomic orbital, we know that your P subshell is higher in energy compared to your S orbital. So you have 2s right here, so that's for atomic orbital, and then you have your 2p right here. Okay, and you're probably wondering, so why are you drawing 3 lines or boxes, right? So if you think about the p orbital, you can actually fit 6 electrons inside this box, and this box, right? So 6 electrons is the max for a p orbital. That's why it's 3 lines right there. Okay, so we know that within the molecular orbital, we have sigma bonds and pi bonds, right? And we also have bonding and anti-bonding. So within the s orbital, we have sigma. So this is sigma 2s, and a higher energy level, which is sigma anti 2s. Right? So the only difference between sigma 2s versus, which is the bonding, versus sigma anti 2s, it's really about the interference. So when they overlap, whether it's constructive or destructive interference, because remember, molecular orbitals are like wave-like patterns, right? So that's sort of how you group them based on its energy level. Okay, typically they would have like a dashed line here connecting, but I'm not gonna do that right now because this is very time consuming, but just keep in mind that this is based on the atomic orbital of 2s for these two. And then if we go to 2p, remember we have pi for the p orbital, right? Because the p orbital can actually have pi bonds. So that means you're going to have sigma anti. This is now for 2p. And then we have, so this is just 1. And we have for pi anti, so this is 2p, and then also we have pi, which is just 2p for the bonding, and sigma 2p. Okay, so hopefully that wasn't too confusing. Let me just move this up just so we make sure. And just so you're wondering, why is it that sigma bonds are higher in energy level compared to pi bonds? Well, sigma bonds are actually more stable. That's why you have it on a higher energy level. Sorry, the other way around. You have sigma bonds, right? So why is it that sigma bonds are lower in energy level compared to pi bonds, as you can see here? That's the first question you need to remember. So sigma bonds are lower in energy because they're more stable. That means it's harder to break sigma bonds compared to pi bonds. Does that make sense? So that's why pi bonds are more unstable compared to sigma bonds, and therefore they're higher in energy. Okay, so for anti-sigma versus bonding for sigma. So why is it that anti-bonding is actually higher in energy? Again, because it's more unstable compared to sigma bonding. And the same thing applies for pi anti, which is right here, and for pi bonding. So that's how you kind of remember the order. And because we're going to use the same diagram all over again until we get to carbon, we're just going to quickly copy this. Okay, there we go. So I'm looking at F2 right here. So for F2, I will be using a red pen, just so everyone can follow, in terms of indicating your electrons in your orbital. So for F2, we know that it's 14 valence electrons, right? And we know that it's 2s2, 2p5. So the first thing you actually do is you fill out your atomic orbital. So you know that you have 2 electrons in your 2s orbital, right? Because that's 2 right here. So you have the up spin, and then you have the down spin. So again, your Hund's rule will always apply here. So that means you fill in your degenerate orbitals first, or your lower energy orbitals, before you actually move on to higher energy. Okay, so for 2p5, because it's 5, right? Again, you need to fill each of your orbitals singly with the same spin, and that would be up spin, right? So that's 1, 2, 3. Okay, that's up spin. 4, and then you have 5. Does that make sense? And then the same thing applies for atomic orbital on the right side, because it's the exact same thing. So you have 1, 2, 3, 1, 2, and then you have 1, 2, 3, 4, and then you have 5, right? So we figured out atomic orbitals, right? So we have 2s2 and we have 2p5. And then for your molecular orbital, because you have 14 valence electron, you start from the lowest energy level. And again, Hund's rule apply. That means you have to fill in your orbitals with the same spin first before you go ahead and put the opposite spin. So 14, so we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, and then you stop there. So that means your last arrow should be at pi anti-bonding 2p. Okay, so first we have to figure out which is the bond order. Sorry, not which is the bond order. What is the bond order of F2? So for the bond order of F2, we have this formula, which is half of the number of electrons in your bonding orbitals. So I'm just going to write bonding here, but that means in your bonding orbital. So you're specifically looking at this molecular orbital and you're trying to figure out the number of electrons anywhere that doesn't have any asterisks. So you have minus and you have number of electrons in anti-bonding. So I'm just going to write anti for simplicity. Okay. Okay, so we're just gonna do a head count. So we have half, right? And then if you look at bonding, that means you're counting this. So that's 2, 4, 6, 8, and that's it. So you only have 8 electrons in your bonding orbitals. Minus anti. So anti would be anything in your molecular orbital that is not highlighted in yellow. So that would be 2, 4, 6. Okay, so that's half times 8 minus 6, right? So that's equal to 1. Does that make sense? So your bond order for F2 is actually equal to 1. And because when you're writing the test, right, or any other midterm, that means time is really constrained. So you can't really draw this whole diagram again. So what I suggest students to do is to have F2 plus. So in this case, you have F2 plus right here. So draw the electrons on the side. So you don't have to go back again and draw your molecular orbital diagram. So just use a different color. So let's try blue. So now we're going to figure out the bond order of F2 plus. Okay, so for F2 plus, right? Now the valence electrons will be different because now you have a plus charge, right? So let's start off by writing the valence electrons of F2 plus. Okay, so the valence electrons of F2 plus is simply going to be 7 times 2, and then you have minus 1, right? Because of that plus charge, remember, it has a tendency to lose electrons, right? If you have a plus charge, because it's a cation. And then you have 7 times 2, 14 minus 1, which would give us 13. So because this is 13, that means your electrons in your molecular orbital diagram, or MO in short, you would have to just have 13 electrons, right? So we're starting from sigma 2s because that's the lowest energy orbital. So what I'm doing is I'm just gonna draw it on the right side, right here. So 1, 2. So we need to fill this and make sure it's 13, right? So this is 1, 2, 3, 4, and we have 5, 6. So in this case, that would be, there's going to be 2 lines here for the blue part. So that's 7, 8, 9, 10, 11, 12, 13. And then you stop there. So as you can see, you have, for bonding, let's just count the number of electrons in your bonding orbitals. Let's use a different highlighter. Okay. Hopefully this isn't too shocking. Okay, so this is, let's see. Sorry. So we're starting from sigma 2s, so that's bonding. So that's 2, 4, 6, and then you have 8, and that's it. So you have 8 electrons in your bonding orbitals, right? So that's going to be right here. So this is 1/2 times the number of electrons in bonding, that's 8, minus, for anti, that means anything that's not shaded in green, and it has to be in the blue pen, right? So we have 2 and 2, 4, and that's 5, right? So that would be 8 minus 5, which is 3. Does that make sense? So you have 3 times 1/2, which is equal to 3 over 2, and that's equal to 1.5. So the bond order of F2 plus is actually 1.5. And then, because I'm on this topic, right? So first of all, how do you identify whether something is paramagnetic or diamagnetic? I know this topic has nothing to do with this question, but because I'm going over the molecular orbital theory stuff, for paramagnetism, right? If you have an unpaired electron, so say for example, this blue pen right here, so you have this one electron which is unpaired, that means F2 plus is actually paramagnetic. So if you have unpaired electrons, that means it's paramagnetic. And if you have paired, which is found in F2, it's diamagnetic. Okay, so as we can see, F2 and F2 plus being compared for bond order. So bond order of F2 plus is actually greater compared to F2. So the first one is actually incorrect because we know that F2 plus this bond order is greater compared to the bond order of F2. Okay, does that make sense? So let's see what they wrote. Yeah, so they wrote F2 plus is greater compared to F2 for the bond order. So this is right. Yeah, it's just that I just like visuals a lot, and it's just easier for me to count. So that's why I'm showing this to you. Okay, so we just have to go through this for oxygen, nitrogen, and carbon. I know this is a lot because this is really a long question. Okay, so now we're transitioning towards oxygen. So for oxygen, it's going to be the same thing. You have to figure out the number of valence electrons, and you have to figure out your electron configuration, but only at the n is equal to 2 energy level. So let me just write atomic orbital, so AO, just to keep it in short. And this is MO, which is molecular orbital. And then on this side, which is atomic orbital. So O2 minus, right? Actually, let's start with O2 because it's your neutral state. So O2, we know that the valence of O2 is going to be 6 times 2, right? Because oxygen is found in group 6, and then you have 2 atoms of oxygen, so 6 times 2, which is 12. Hopefully that makes sense so far. So we have to figure out the number of valence electrons and also your electron configuration, but only at the valence, which is 2. Okay, so we have this, right? But for your electron configuration, right? Only at n is equal to 2. So let's go back to our periodic table. So oxygen is found beside fluorine. So oxygen is right here. Hopefully this periodic table isn't too small. So oxygen is right here. So as you can see, it's actually 2p4, right? So 2s2, 2p4, right? So that means this, we have 2s2, 2p4. Okay, so we start indicating our electrons for our atomic orbital and, both on the left side and on the right side. Okay, so we have this, so it's in red. So 1, 2s2, and then you have 2p4. 1, 2, 3, and then we have 4. Again, Hund's rule apply here, so that's why I'm filling each of them with the same spin first. So 1, 2, 3, and then 4. By the way, you can also put it right here, as long as you make sure you have up spins for each of your subshells right here. Okay, so in this case, but because I want it to be consistent, I'm just gonna put it on the left side. Okay, so in this case, we have 2s2, 2p4, so atomic orbital of O2 is done. Now we move on to molecular orbitals. So we know that there's 12 valence electrons. That's why we need to fill this with 12 electrons. So 1, 2, starting from the lowest energy orbital. So we have 4, 5, 6, 7, 8, 9, 10, 11, 12. So as you can see, for oxygen, you have to stop at pi anti 2p right here. That means this is paramagnetic, right? Because you have 2 unpaired electrons. So now let's look at the bond order for O2. So the bond order of O2 in this case is going to be 1/2, right? Times the number of electrons in your bonding, right? So let's keep it consistent. So let's turn this into yellow. So bonding, you have 2, 4, 6, 8. And yeah, I think that's pretty much it. So we only have 8. And then for anti, we have 2, 3, and then we have 4. So this is actually equal to 2. And then if we go and look for O2 minus, right, because that's the next one. That means you have to have 1/2 and then whatever the number of electrons here for bonding is minus anti, right? So for your valence for O2 minus, that means you're going to have 6 times 2, right? Because oxygen is found in group 6 and you have 2 atoms of oxygen plus 1 because you have minus 1 right here as the charge. And you would end up with 13. So it's really the same as compared to fluorine as we were working on earlier. So valence electrons is 13. So that means you're going to fill this with 13 electrons. So this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's it, because it's only 13, right? So for bonding, we have, so this is, oh my goodness, okay, sorry. That was the pen. I just realized. Okay, so highlighter here, it's in green. So bonding, there's 2. Then you have 4, 6, and then you have 8, and that's it. So you have 8 electrons in your bonding orbital. And then for anti, that means anything that is in blue pen but it's not highlighted. So you have 2, 4, and then you have 5, right? So again, this is 1.5 because it's 8 minus 5, which is 3 times 1/2, that's 1.5. So comparing O2 and O2 minus in terms of the bond order of O2 is greater compared to O2 minus. So this should be the other way around, right? Okay, we're almost there. I know this is very lengthy, but this is the way to go. So we have nitrogen and carbon. I know this is a little bit of my rant, but I just really appreciate the person or the people who actually invented copy and paste. Like, can you imagine I was able to paste this? Otherwise, we would have to draw this again. Yeah, so going back to the question, we have nitrogen. So this is N2 minus, and then you have N2. So I like to start with the neutral nitrogen. So in this case, valence electrons, that would be 5 times 2 for nitrogen. So this is 5 times 2, and why is it 5 times 2, which is equal to 10? Well, nitrogen is found in group 5, right? So if it's found in group 5, therefore it has to have 5 valence electrons. So nitrogen is right beside oxygen right here. So it's highlighted in blue. It's atomic number 7. Hopefully you guys can see that. Okay, so 10 valence electrons, and going back to this periodic table, that means nitrogen is actually 2p3, right? 2s2, and then you have 2p3. Okay, so 1, 2, right? 2s2, and then you have 2p3. 1, 2, 3, and that's it. You stop. Same thing for this side. Oh, and by the way, this is your atomic orbital, and this is your atomic orbital. On the other hand, you have your molecular orbital, which is in the middle. So it's the same thing. So 10 valence electrons. So here we go. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so this is 10 valence electrons. We stop there, right? So that means your bond order for N2 is equal to 1/2 times bonding. So you have 2, 4, 6, 8, right? So that's 8 electrons in your bonding orbital for N2 minus anti. So anti would be 2, and that's it. So you only have 8 minus 2. So you have 6 divided by 2, which is 3, right? So the bond order of N2 is actually 3. Does that make sense? If you do have any questions, please get in touch with me, and we'll figure this out. Okay, so this is BO N2, and that's equal to 3, right? So now we move on to N2 minus. Okay, I think I realized that I switched up the colors. If you guys are very meticulous, I think I did switch it up. So I placed the neutral atom, which is in blue, so just bear with me, but this is N2. Okay, so we have bond order of N2 minus for the next one. So you guys know we need to find the valence electrons of N2 minus. So valence electrons of N2 minus is 5 times 2 plus 1, which is 11, right? So if you have 11 valence electrons, that means your molecular orbital diagram needs to contain 11 electrons, right, in total. So you have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, and then you stop there, right? So you stop at pi anti 2p. Okay, so again, we're going to count the number of electrons in bonding and anti for N2 minus. Okay, so here we have 2, right? And then we have 4, 6, 8. And that's it. So we have 8 for bonding. So 1/2, 8 minus anti. So for anti, there's 2, right? And then you have 3. So it's 8 minus 3. So that means if you have 8 minus 3, right, times 1/2, you should be getting 2.5. Yeah, because it's 5 divided by 2, right? Which is 2.5. Let me just double check that. Okay, 2.5. Okay, that's it. And then we have N2 and N2 minus for your bond order. So bond order of N2 is actually greater compared to N2 minus. So they're saying that bond order of N2 minus is greater compared to bond order of N2. Well, this is false, right? Or this is incorrect because N2 is greater compared to N2 minus. And let's see what they said so far for oxygen and also for nitrogen. So for oxygen, they're saying that O2 is greater compared to O2 minus, and this is right. Now, if you go and look at nitrogen, right, they're saying that nitrogen is, let's see. Okay, so they're saying that N2 plus and N2 minus are the same, right? Because the question gives us N2, which is the neutral dinitrogen atom, right? Versus N2 minus, then we didn't really solve for N2 plus. So that's why this one would hold true, right? Because we're just looking at the neutral state. So there might be a typo in this. Hopefully that makes sense because they're looking at N2 plus, right? And we're looking at the neutral dinitrogen, right? So that's why it's different. However, they're looking at N2 minus as well, and we're also looking at N2 minus. But then we're comparing two different things, right? So I would stick to this. N2 and you have N2 minus. And then you have C2 minus and C2, right? Okay, so we're gonna do the copy and paste thing again, so we don't have to draw this one more time. Okay, now we're looking at carbon. Okay, so carbon, basically valence electrons of C2. I'll start with C2. So valence electrons is going to be 4 times 2, which is 8. And how do I know it's 8? Well, carbon is found in group 4, right? So carbon is right beside, it's on the left of nitrogen, as you can see. And going back to this periodic table, we know that carbon is actually 2s2, right? 2p2. So 2s2, let's just fill that, right? 2s2, right? And then you have 2p2. Okay, same thing. Again, this is atomic orbital. This is molecular orbital, and then you have atomic orbital. 2s2, then you have 2p2. And because you have 8 valence electrons, you need to fill your entire molecular orbital diagram with 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, right? And then you stop there. Now, bond order of C2 is going to be 1/2 of your electrons, right, found in your bonding. Okay, so this is 2 right here. And you have 4. Then you have 5, 6. So for carbon, there's going to be 6 for your electrons in your bonding orbital. And then for anti, that's just 4. Right? So 6 minus 4 is 2 times 1/2, that's equal to 1. So bond order of C2 is equal to 1. Sorry, this 4 should be 2, right? Here, there's 2. I did that intentionally, so I just want to make sure you guys are paying attention, so... No, I'm just kidding. So this is 2, right? So basically you have 6 minus 2, right? And then you have times 1/2, and that's 4 divided by 2, which is 2. So bond order is 2. I stand corrected. Okay, there we go. So this is 2, and moving on to C2 minus. Bond order of C2 minus, again, we're looking for the valence electrons. Okay, valence for C2 minus is 4 times 2 plus 1, right? Because we're adding 1 electron. So that's 9, right? So if you have 9 in total for valence electrons, that means you need to fill this with 9 electrons. So 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So you stop here. And then you go ahead and count your number of electrons in your bonding orbital again. I think I've said so many times we need to count bonding orbit, like number of electrons in your bonding orbital and anti. So hopefully this gets drilled into your head by now. So this is 2, right? And then you have 4. So that's in green. 4, 6, and then you have 7, right? So there's 7. So the number of electrons in your bonding orbital is 7. So 1/2 times 7. Then you have minus anti, right? So anti electrons, there's 2. So that's 5 divided by 2, which is equal to 2.5. So as you can see, the bond order of C2 minus is greater compared to the bond order of C2, which is 2. So the bond order that is correct would be the last one, right? Which is C2 minus is greater compared to C2. Okay, so just to make sure that what we have here on homework help is right. So they're saying C2 bond order, that's... Okay. It's 2, right? That's what they're saying. And then they're comparing C2 and... Sorry, they're comparing C2 minus and C2, right? So C2 minus, they're saying it's greater compared to C2, and therefore this is right. It's the one that I highlighted in blue. Yeah. So this is the right answer. Okay, so hopefully that whole bond order thing makes sense. Yeah, that was a long one, but it's a very popular question, especially when you go to Western. Okay, so moving on to this part. Okay, so this is an interesting question. They're just asking, what is the chemical formula of graphite? So as you know, graphite is basically composed of carbon, right? So it's the same element. However, it's just the way that they're bonded together. So it's more so structural modifications that's different. But it's still what you call an allotrope, right? Again, what is an allotrope? So an allotrope is a modification in the structure, but it's composed of the same element. So as you can see right here, right? So this is the structure of graphite, which is right. And you have carbon atoms, right? So they're bonded differently. And that's why the chemical formula of graphite is just simply carbon, which is just C, right? Because it's all composed of carbon and nothing else. So that's why it's C. And this is right. Okay, so that was a quick question. Moving on to this one. Okay, so we have to calculate the pH of a 0.20 molar solution of NH4Br, and you need to show your work clearly. So what they've presented is basically they're saying that NH4Br is an acidic salt, and then it will react with water under hydrolysis, right? So first of all, what is hydrolysis? So it's the reaction of water, and water is the reagent that is responsible for breaking the bonds of whatever reactant it gets paired with. So that's what hydrolysis is, and it forms NH3 and H3O+, which we know is the hydronium ion, which is right. And then it says before you can actually solve for the pH, you need to first figure out what the concentration is of H3O+, right? There should be a plus here. And in order for you to do that, you need to find the Ka of NH4+, which is the ammonium ion. And if you do have the Kb expression, okay, so this is where things switch from Ka to Kb, right? So for this question, first of all, you need to be given your Ka for NH4+ or your Kb for NH3. So either one is fine. And then the way that you're supposed to solve it is dependent on whether you're starting off with NH4+. Does that make sense? Okay, so bear with me. I know we still have like 5 minutes left, but I want to get through this question. So let's just deal with this. Okay, so we have to find the pH of NH4Br. Okay, so as I mentioned, we have what you call your ammonium and your Br minus in this case, right? So this is NH4 plus and you have Br minus. So we know that this NH4 plus is, so if you see the 0.20 molar, that means that's your concentration for NH4 plus. And how do I know that? Well, we know that for this NH4Br, right? So what this answer is saying, it's an acidic salt, right? So first we have to figure out whether it's truly an acidic salt, right? So that means the pH is acidic, right? Lower than 7. So how do you even figure that out? Well, in this case, you have NH4 and Br, right? So the whole assumption here is you need to think about if NH4Br is a strong electrolyte, meaning it's going to undergo hydrolysis, right, which they mentioned. But then the problem here is if you look at Br minus, we know that HBr is actually very acidic, right? It's one of the 7 strong acids. That means this will not undergo hydrolysis, right? So first of all, there's 2 important points that you have to remember. So if your anion is part of one of your strong acids, so let's say if you have Cl minus and it gets paired with H, right, which is hydrochloric acid, HCl, if it forms a strong acid, that means this anion will not undergo hydrolysis. Does that make sense? And then if you have NH4 plus, right, because even though this is a cation, but it's not a metal, right? So in that case, this means it can undergo hydrolysis, right? So we have NH4 plus and you have water. So this is just your Bronsted-Lowry acid and base equation, right? So we have water and then we have NH3, which is ammonia, which is the base. And then we have H3O plus, right? How do I know it's H3O plus? Well, this is your acid, right? From this equation. And then this is your base, which is water. Now what's your conjugate acid? Conjugate acid would be, so Ca is H3O plus and NH3 is your conjugate base. Does that make sense? So that means if you have H3O plus here, that's what you need to have, that's what you need to solve for, right? Concentration of H3O plus. And that's why you know that you're going to start off with NH4 plus. So because it's an equilibrium expression, we can say that we're looking for Ka, right? So if you check your textbook, and this should be given during the test, so not to stress about, if you have your Ka, which is equal to, so for NH4 plus, the Ka is equal to 5.6 times 10 to the negative 10, right? That means when you write your equilibrium expression, based on the chemical equation of NH4 plus, you're going to see that you can write your product over your reactants, right? So this is NH3, that's the concentration multiplied to the concentration of H3O plus. And this is all over the concentration of your product, which is NH4 plus. And first of all, you're probably wondering, or in case you might forget, that if you're looking at H2O, we know that this is in a pure liquid form, right? It's not really affecting your equilibrium constant or your expression. So that's why we don't have it right here, because it's equal to 1, right? That's the concentration. Okay, so you're going to set up your ice table here, but we can just assume that because you only have 1 mole of NH3 right here, and you have 1 mole of H3O plus, that means you can actually say that this is x squared, right? So this is x squared over NH4 plus. So the concentration of NH4 plus is actually equal to 0.20 molar, right? So we can just write that down. And then this is equal to your Ka, which is 5.6 times 10 to the negative 10. Okay, so I'm just dropping the molar just for simplicity. And then what I'm doing is I'm multiplying 5.6 times 10 to the negative 10 with 0.20. And then I'm taking the square root after that. Okay, 5.6 times 10 to the negative 10 times 0.20. And that's equal to 1 point. So if you multiply this, you would get, you would get 1.12. Times 10 to the negative 10, and that's equal to x squared, right? And then you're taking the square root of both sides, right? So taking the square root of both sides, you would get 1.058 times 1.0583 times 10 to the negative 5, right? So in that case, you would have your x being equal to this, right? So what did we say what x was? So we said that x was NH3 and H3O plus, right? So we know that the concentration of H3O plus is this thing, right? Or this number. Okay, so once we have that, all we have to do is we have pH, which is equal to the negative log of 1.0583 times 10 to the negative 5, right? And then when we take the negative log of that, that should give you 4.97, which we have that right here. I've highlighted, and that's right. So this is 4.97. Taking into account the number of significant figures, which is 2, right? So 4.97. Okay, so that's the pH. And alternatively, because they brought up Kb, right? So Kb right here, they said it was 5.6 times 10 to the negative 10. This should be Ka, not Kb, because we're dealing with NH4 plus. So this is Ka, and that's equal to NH3 times H3O plus divided by NH4 plus, right? So they've pretty much done it this way, which is similar to this, but the only correction I would say is this should be Ka. But if you're given Kb, for instance, which is Kb of ammonia, right? Okay, let's scroll down. So let's say the Kb of ammonia, because it's a weak base, right? So if your Kb, so I haven't really written that down, but if you have this information, which is 1.8 times 10 to the negative 5, right? You still have to use your Ka, right? You can't use this and be like, okay, this is my Ka. No, this is Kb, right? So that means you have Ka, you would have to use this equation, which is Ka times Kb, which is equal to Kw, right? Equilibrium constant for water, right? So this is 1 times 10 to the negative 14. And this is equal to Ka times Kb, right? So we're solving for Ka in this case. And that's 1.8 times 10 to the negative 5. And then once you solve for Ka, right? So dividing both sides with 1.8 times 10 to the negative 5. So this is going to be equal to 5.6 times 10 to the power of 18. Okay, hold on. This should be, sorry, on my calculator I have raised to the power of 14. That's why we're getting the wrong answer. Okay, now it's right. So make sure this is negative 14. Okay, so times 10 to the negative 14 divided by 1.8 times 10 to the negative 5, that's equal to 5.6 times 10 raised to the power of negative 10. Okay, now this is consistent to what we had initially, right? As you can see here, let me just highlight that. Okay, so that's your Ka for ammonium, and that's the same thing right here. Okay, so before we wrap up, I just wanted to say thank you so much, guys, for coming in. You know, I know probably school is the last thing that's going on in your mind right now. Obviously, health and safety is first, but I guess I just wanted to instill that hopefully, and I think everyone just hopes that things will resume back to normal, and I'm just really concerned. And OneClass is here for you, and we're really concerned that you know, you need to be on top of your studies, because at the end of the day, once this all goes back to normal, you're going back to school, and that's not